Because of how alternating series work, we have a nice way to figure out the remainder or the error if we have computed a partial sum of an alternating series. That way is given to us by the Alternating Series Estimation Theorem, and it says that if S is the infinite sum of a series -1 to the n minus 1 b sub n, where b sub n is greater than 0, and the sum of an alternating series that satisfies the alternating series test. That is, the terms are decreasing in magnitude. B sub n plus 1 is less than b sub n. I guess we said less than or equal to, didn't we? And the limit as n approaches infinity of b sub n is equal to 0. Then the absolute value of the remainder sub n, right, r sub n, is equal to the absolute value of s minus s sub n, and that's less than or equal to b sub n plus 1. How does this work? Well, let's prove it and you'll see. We already saw that the sequence of even partial sums s sub 2n is bounded above, so the sum s is greater than s sub 2n. A similar process would yield that the sum is less than s sub 2n plus 1. Thus, S is between two consecutive partial sums, let's say S sub n and S sub n plus 1. At this point, I'm going to step away from the proof and bring back a picture we saw before. So we just wrote down that S is between two consecutive partial sums, and in this diagram here, you can see that S is between S1 and S2. It's also between S2 and S3. It's also between S3 and S4. Suppose we pick two of these. Call one of them S sub n and one of them S sub n plus 1. I guess it didn't matter in what order I did that. The distance between S and S sub n is smaller than the distance between S sub n plus 1 and S sub n because S is between the two. So let's write that as an inequality. This implies that the absolute value of S minus S sub n, because we don't know which one's on which side of S, right? We're just saying the absolute value is less than or equal to the absolute value of S sub n plus 1 minus S sub n. But folks, the difference between S sub n plus 1 and S sub n is simply one term, and that term is B sub n plus 1. Now let's put this together. We said that the remainder is the absolute value of S minus S sub n, and we just showed that that is less than or equal to B sub n plus 1, thereby concluding this proof. In words, the size of the remainder of a partial sum of an alternating series does not exceed the size of the first neglected term. Let's see how we can put this to use. We're presented with a series. The sum as n goes from 1 to infinity of -1 to the n minus 1 times n over 8 to the n, and we're asked to estimate the sum correct to 4 decimal places. I leave it to you to verify that this does converge by the alternating series test. And the terms of this series look like, so I'm giving squiggly equals, right? We're estimating. So approximately 1 over 8 minus 2 over 8 squared plus 3 over 8 cubed minus 4 over 8 to the 4th plus 5 over 8 to the 5th plus ... And the question really is, how many terms do I need in order to be as close as as is specified? Well, we want r sub n in absolute value to be less than 0.0001, right? It's correct to 4 decimal places. So what I need to know is, which is the first term that's smaller than 0001? Because once I know what that term is, I add all the ones up to that one, but I don't include that one. Turns out that b sub 5 which is equal to 5 over 8 to the 5th, is approximately 0.0002, which is not less than 0.0001. So we'll need at least up to 5 terms. b sub 6 is 6 over 8 to the 6th, and that's approximately 0.00002, which is less than 0.0001. We want to be correct within 4 decimal places, and we're good with 0.00002. Therefore, we don't need this one. We don't need b sub 6. So, adding together the first 5 terms, we get that the sum is approximately 0.0988. And please resist the temptation to write more digits. We were asked to be correct to 4 decimal places. That means we stop once we get to 4 decimal places.